afterwards and beg for mercy, or maybe you're like, hey, I actually earned a 95 and you wrote 59, or something like that. I mean, it happens, so you might want to double check that I added things up right. It doesn't usually happen, but just in case. So you've got your exam there. Let's see, here we go. Okay, here, so compare, determine whether each series converges or diverges. So I jotted down a few notes. There are probably other complaints I had, but I graded this on Saturday and I forgot about all my complaints. So you're making a comparison. You've got a couple of choices here. It's either the limit comparison test or the direct comparison test. Most of you chose to use the direct comparison test. Actually write down the comparison. Write it down, which means this thing is less than this thing. N goes from 2 to infinity of 1 over n squared. Write down your comparison. So that's less than a convergent, and then tell me that that converges. So it's less than a convergent power series. And then this one, how would you compare? Well, you've got a bunch of things you can compare this to, but the thing that kind of pops out to me is that this is bigger than this. 1 over 5 times 3/2 to the n. Now, just to be clear, you could have, a lot of you decided to compare this to this. This is not a true statement. So if you wrote this down, not true, sorry. This is true, but if you really insist on comparing it to this, don't use the direct comparison, use a limit comparison. Using a limit comparison with this would be easy, but either way you find that that thing diverges because it is bigger than, did I have bigger than there before? I hope so. It's bigger than divergent power series. Yeah, I don't know if I had a bigger than there. Let me just back up. Oh yeah, I did have bigger than. Good. Okay, so there's that. That's a minor complaint. Okay, here. With this, if you're going to do this ratio or root method, write the limit. Write the word limit. Do it. Humor me, even though you don't want to. Use that limit and do the limit. So you're doing a limit as n approaches infinity of whatever it is. Here it's the nth root of 2 plus 3n over 2n squared plus 9 to the n. And then you could just say that equals 0. Some of you thought that equaled 3/2. It does not. It equals 0. Okay. So then that converges. Converge. There. There we go. Okay, that's enough. Okay, so endpoints. Do the endpoints when you're doing the interval of convergence. I know you don't want to, but unless this is a geometric power series, which neither of these are, you have to do the endpoints. Now, here's what I mean by geometric. These are geometric. You don't have to deal with the endpoints because you know that geometric series do not converge at their endpoints. Or maybe you don't, but we can pretend that you did. But up here, you can't pretend because, in fact, this one, it converged at both endpoints. I know, wasn't that mean of me? This one only converged at one endpoint and not at the other endpoints. You have to check the endpoints, so be sure you do that. Okay, let's see. Seems like it's just coming back to me, something else that really bothered me. I know, it's like I get bothered by so much. Okay, these are geometric, which means hopefully you know that, yeah, if you need help with these, but this one especially was challenging for some of you, so let me just write it out really quickly. X cubed over 3 times the quantity 1 over 1 plus 2/3 x. Double check. One of the things I love about math, I was just bragging to my Calc 1 students about this, because we're doing substitution, and you know what's great about substitution is you can always be 100% sure that you've got the right answer. And the reason why is because after you do your antiderivative, just do the derivative, and you can check. So same thing goes here. Double check. Some of you wrote down all kinds of crazy stuff at this stage, and all you would have to do is multiply, and you find, oh, it's not, this one is the same. Multiply through, and you get this exact expression. But anyway, once you have that, the rest, where to go? There it is. The rest of this is pretty straightforward. I'll just do the next step. This is x cubed over 3 times the sum where n goes from 0 to infinity of negative 2/3 x to the n. Negative 2/3 because you need a negative here. It's 1 minus the negative of that stuff. But anyway, you can work this out on your own. Hopefully, this one is like the reverse of this. So if you could do this, then you should be able to do this. These are geometric series, both of them. And so this one, I was especially disappointed if you didn't do part A right. Here's what you would do. You do 88 times 1 over 1 minus 22/23. And if you didn't do it right, do it now. Do it on your calculator if you can't handle the algebra, and you'll find that the answer is a fun answer. This one, not so fun. It was 1/5. But it's 2. There are 2. You have the sum where it goes from 0 to infinity of 1/2 times 1/2 to the n minus the sum and goes from 0 to infinity of negative 1/4 to the n. So you ended up with 2 separate geometric series, but you can deal with them using the same formula. Use the formula. Okay, is that it? Yeah, there's probably other things that made me cranky. Oh, this one. Come on! Is it because I didn't bring my mug? Come on. You should know this by now. You know this is on every single test. Come on. Integral of 1 over x squared plus 1 is arctan. Some of you are like, even now, you should know this by now. Some of you are using the natural log of x squared plus 1. I know, good guess, if you hadn't been in my class for the past however many months. Anyway, that's enough of that. Okay, I gotta calm down here. Okay, I think that's it for now. But like I said, those were my complaints. If you have complaints of your own, which you might have some valid complaints. I'm getting hot. I need to take this off. So if you do have some complaints, feel free to stick around afterwards. Make sure I've stopped the recording because you don't want all your friends to hear about you begging for 1 point or whatever it is. But I'm happy for you to beg. It's okay. So there. Yeah, so stick around if you want to. Otherwise, we're moving on. We're moving on. Look at this. So exciting to something new. Taylor and Maclaurin series. This is the last topic. It's going to last 2 weeks. We're going to start slow, though. So we'll take our time with this. Don't worry. So let's take our time. In fact, today, we're basically only going to do 1 problem. We might, no, that's not true. We might do 2. We might do 2 problems, but that's it. I'm not doing more than 2 problems, I guarantee it. So here is what we're going to do, is remember that power series, at least up until now, they all came from this expression, right? So, I'm going to have to switch over. I'm going to have to switch over to this because it's going to annoy me that I can't scroll. So here, hold on a second while you're doing this. So power series, here, do this for me. 1 minus x is equal to what? What is that power series? So figure it out while I get myself set up. There we go. Lovely. All right. Back here, up 2. I know you all know this, but Andrew wants to show off. So Andrew, what is the power series representation of 1 over 1 minus x?
From n equals 0 to infinity of x to the n.
X to the n, beautiful. So this is the sort of the basic starting point for all of our power series. And in fact, we had things like this, 1 plus x squared, which I know now this is going to trigger. You're going to have like this. Every time you see that, you're going to be like, no, he's going to be angry at me. No, I'm not. So anyway, this is related. N equals 0 to infinity of negative x squared to the n. So you know the deal here, 1 over 1 minus, let's do, how about 5x? If you have something like this, you're just replacing the thing in the parentheses. It's all based on this geometric series. So up until now, we've been stuck with geometric series. Geometric. But there are a lot of functions that don't look like this. Let me show you some examples. What about this function, e to the x? So f of x equals e to the x. I would like a power series representation of that function. So that's our goal for today. In fact, just to prove it to you, let me put the PowerPoint back up here and you can see f of x equals e to the x. That's the main thing that we're going to deal with. I'll probably show you some of this PowerPoint in just a minute, but let's work on this. This is going to take the bulk of the time, is to deal with this. So f of x equals e to the x. Now, what we want is we want to be able to do something like this of, let's see, we're going to have a sub n times x, I don't like a anymore all of a sudden. Let's use a little b. X minus a to the nth power. This is sort of the general form of a power series. You have some numbers times x minus a to the nth power. And we haven't really spent a lot of time dealing with power series that are not centered at 0, but it's not that difficult. In fact, I probably should have had one more example up here. Let's do one more. Let's get rid of that erasure, or erase that line. Let's do 1 over 1 minus x plus 3. That's going to be the sum where n goes from 0 to infinity of x plus 3 to the n. And the big deal about that one is that when you have a power series, which you had at least one that was like this on your test, if the power series is not x to the n, if it's x plus 3 to the n, then it's no longer centered at 0. So for example, this has an interval of convergence from negative 1/5 to 1/5. You're just going to have to trust me on this. I mean, you could work it out yourselves, but that's going to take some time. And then this one, x plus 3 is between 1 and negative 1. So that means that x is between 4 and negative, or not negative, 2, positive 2. So it just shifts the interval of convergence over by 3 units. I just did my arithmetic incorrectly, didn't I? Sorry, I'm so excited about the e to the x that I was just getting a little off track there. Okay, so you have that. So getting back to this, this is our goal for today, is to get the power series, and we will have it shortly. I mean, seriously. And I've got a video to show you. You're going to love it. But anyway, getting back to this, this particular power series, let's just say, for now, let's center at a equals 0. So just to make things easier, don't worry, we'll make it harder again just momentarily. So let's say that I want to do this. E to the x is equal to the sum where n goes from 0 to infinity of b sub n times x. To the n, sorry. Okay, so that is centered at 0 now. Now here's the thing about this. It looks like how are we going to be able to figure this out? You might say it seems impossible, but the interesting thing about this is that you can actually figure out what the b's are. Oh, here, let me rewrite it one more time. So you have b0 plus b1x plus b2x squared plus b3x cubed plus b4x to the fourth, etc. I think that if you spent a little bit of time doing a little bit of algebra, you could figure out what all of those b's are. I'm so confident, well, I'm not that confident. I just don't want to take the time. It would take you probably half an hour. Some of you could do it in 5 or 10 minutes. Some of you would take a little bit longer. So I'm going to give you a little bit of a hint to help you, and then you'll be able to do it for me. So here's my hint, and that is that if you pick a value for x, if this was true, it's going to be true for every value of x. Right? If this function is equal to this function, it'll be true for every value of x in the interval of convergence. And we'll get to that in a bit. But in particular, this will be true for x equals 0. So when you put x equals 0 in here, you get e to the 0 is equal to b0 plus b1 times 0 plus b2 times 0 squared, and so on. Which means that b0 is equal to 1. How easy is that? Okay, maybe it's not that easy, but you've got your answer there. Okay, next, let's get b1. Well, let's see. Now here's where things get complicated, because if I pick another value for x, let's say we use x equals 1. That seems like it would be easy. Ooh, with x equals 1, you end up with e to the first, is equal to b0 plus b1 plus b2 plus, it goes on forever. That's no good. So what we could do, though, is take this original function, and let's do the derivative. So let's do the derivative of this function. In fact, here I'm going to grab this whole thing. Give me a sec. Duplicate it and put it down here. Let me draw a line so that you don't think that I'm starting fresh now. We've got our b0, so I suppose I could write that in, couldn't I? There. How's that? Here's what I would suggest we do. Let's take this function and do the derivative of the function. And do the derivative of this side. We could do that, couldn't we? In fact, I know you can do this. Caden, what's the derivative of e to the x? E to what? Oh, e to the x. Okay, sorry. It's my poor hearing from being in chapel too often. So there it is. So e to the x, very nice. So we know the derivative of e to the x. And so it's our favorite function, some of you. And then we just need to do the derivative of this nasty long thing here. But I'll bet we can do it. Mariah, what's the derivative of 1? 0, very nice. Okay, who's next? Jackson, what's the derivative of b1x? If the b1 wasn't there, yeah, it's just going to be 1. And now the b1 is there, though, so it's just b1. Like if that was 3x, you would say the derivative is 3. So here it's b1x, so the derivative is b1. Yeah. b1. Okay, now things get a little bit more complicated, but easier, actually. Madison, what's the derivative of b2x squared? What about just x squared? 2x, so throw the b2 in there. Yeah, so 2b2x. Very good. All right, we're almost there. We'll just do 2 more, and then we'll see the pattern, hopefully. All right, next we have Cooper. What's the derivative of b3x cubed? Very nice. Now you're starting to catch on. If you're, anyway, Ethan, last one here, b4 times x to the 4th. Excellent, and I'll bet you can just tell me this. This is going to be 5b5 x to the 4th, etc. I'll just put that there just to show off that you can see the pattern, can't you? You can see the pattern. Okay, now we're going to do the same trick we did up here, and the trick that I'm using is this. I know that x equals 0 is going to make most of this stuff equal to 0, and that's why this worked out so nicely. So let's do the same thing here. Let's let x equal 0. So when x equals 0, you get e to the 0 is equal to b1 plus a bunch of zeros. Okay, so b1 is equal to 1. All right, we're doing pretty good here. Okay, give me a sec. I need to figure out what I'm going to do. I'm going to do this. Here, how about this? Copy and paste. Okay, I'm going to change my notation just slightly. It's not a big deal, so don't get worried that I'm going to just change things up on you. I'm just going to add one thing to all of this. instead of referring to this as e to the x, I'm going to refer to this as f of x. So this is going to become f of x. And only because this will help me with my notation below, because here, instead of writing the derivative of e to the x, I'm going to write it like this, f prime of x, which we know that the derivative of e to the x is just e to the x, right? And so down here, I'm going to write it this way, that f prime of x is equal to this stuff. Notice all I've done here is I've copied this, which we already know is the derivative of e to the x, copied it down here. And now I'm going to do the same thing. Notice I'm just going to do the same thing over and over now, where I'm going to do another derivative. So I'm not satisfied with one derivative. In fact, I'm going to do an infinite number of derivatives. You might say, how could you do such a thing? Well, you'll see. In just a minute, you'll see, hopefully, why I can do an infinite number, theoretically, in my head. Okay, Tyler, let's do the derivative of what's over there on the right. What's the derivative of b1?
0.
It is 0. Okay, Sawyer, what's the derivative of 2b2x? 2b2, very nice. So remember, the b's are all constants. That's what we're trying to figure out what those b's are. All right, Matthew, what about 3b3x squared?
6b3x.
All right, we'll just do one more, and then I'll just wave my hands here. Drew, what about 4b4x cubed? 12b4x squared. Very nice. And then you can probably see that that's going to be 20b5 x to the third. Sorry. And I'll bet you could even guess what the next one is. I'll tell it to you. It's 30b6 x to the fourth. And then I'll just put some dots there. I know, it's kind of a pain. Trust me, we're going somewhere with this. It's going to be worth it. So next, we need to do the derivative of e to the x. Okay? So in other words, what is the second derivative of my original function? Here's my original function. And we did the derivative of that function. It's right there. And now I need the second derivative of this function. And I'll put it over here. So I bet you can do this, though. Luke, what is the second derivative of e to the x? You know, that's the beautiful thing about e to the x, isn't it? That it is its own derivative, and so it's its own second derivative and its own third derivative of e to the x is e to the x. What about the 20th derivative? I'll bet you can tell me what that is. E to the x. This is why I say that at least with this function, I can do this in general, do every one of them, like infinitely. I can go down as far as you want me to. You want me to do the 1000th derivative? E to the x. So nice, this is a nice function. The only thing that is a little problematic is the right-hand side of all of this. The left-hand side is going to be easy because derivative of e to the x is e to the x. The right-hand side looks more complicated, but trust me, you're going to see a pattern here in a minute. Now let's do the same trick. Let x equal 0. Plug it in. Tell me what you get for b2. Take a minute, see if you can work this one out. See if you see what we're doing. And I'll pick a volunteer here. Where did that thing go? There it is. Need my arctangent. Austin, what did you get when you plugged x equals 0 into that previous line? Well, talk me through it. What's e to the 0? 1, that's right. So e to the 0 is 1. And then you're just going to plug x equals 0 into everything over here. And so what's left over when you get rid of all the stuff that has x in it? Yeah, 2b2, right? So that equals 2b2. Everything else, this becomes 0, this becomes 0. All of these become 0 when you plug 0 into this. But I'm left with 2b2. All right, so what's b2? Well, b2 is 1/2. All right, we're doing great here. You tell me what b3 is. Now, let me just, in case, just in case you're not sure how to do this, I'll just review for you what we just did, is we took the first derivative and we did the derivative of the first derivative, which gave us the second derivative. And then from that, we plugged in x equals 0, and that told us what b2 was. So you're going to do the same thing, starting with this. This is the second derivative, and you're going to compute the third derivative from that, which, of course, we know that the third derivative is just e to the x. Anyway, do the third derivative of this nasty big polynomial here, and then we'll see where that goes. All right, let's see where we are with this. First of all, we need the third derivative. So you're doing the derivative of this derivative. So let's see if you can rattle it off for me. Rachel J., what is the derivative? Can you just rattle off the whole thing? Yes, very good. And you probably, it's a little harder to see what the pattern is here, but I'll tell you what the pattern is. This is 1 times 2 times 3. This is 2 times 3 times 4. 3 times 4 times 5. 4 times 5 times 6. So the next one will be 5 times 6 times 7. Anyway, you can probably figure out that pattern eventually. Just like this was just 1 times 2, 2 times 3, 3 times 4, 4 times 5, 5 times 6. Okay, maybe you didn't notice that. Well, I'm telling you now. But anyway, getting down here. So there is a pattern. There's a pattern. You can figure it out. And now, using that, I want to know what B3 is. So you're going to let x equals 0, plug this in. I'll do the left-hand side. So what's the right-hand side? Nolan, what's the right-hand side when you plug x equals 0 into the right-hand side there? 6B3. 6B3. Very nice. And then, Gavin, what is B3?
1/6.
It is 1/6. That's amazing. Okay, so I'm just going to pause for a minute because I want to bring us back to our original goal, because you can get lost in doing these derivatives. The original goal was to come up with a power series representation of e to the x. And here's where we are on this power series. We actually have got quite a bit here, and that is this. We started off, we had 1 plus x plus 1/2 x squared plus 1/6 x cubed. And then we're going to get at least one more. We're going to get at least one more of these, something times x to the 4th. But we're doing pretty good. We've gotten at least, 4 terms? And I don't know if you can see the pattern here yet. I'll tell you what the pattern is momentarily, but let's get back to this, because we're going to do it one more time. One more time. Bear with me. We can do this. So let's see. Do we need to write it all out? No, we don't. E to the x. This is the 4th derivative. I'll write it like that. So the 4th derivative, and you're going to do the derivative of this thing right here. Okay, so let's do this. I bet you can do this on the fly. In fact, I'm so confident. I'm just going to ask Adric. Adric, can you do the derivative of what's highlighted in yellow there for us? That's a 6 there. Sorry, I got so excited. And then there's some other stuff. Very nice. Okay, so we've got that. And then we're going to let x equals 0, which means on the left you'll have 1. On the right you'll have 24b to the b sub 4, which means b sub 4 is 1/24. Let me go back to PowerPoint land. Oh, this is so cool. 1/24, x to the 4th. I'm going to put dots in there. Okay, so does anyone want to take a guess as to what the next one is? Oh, actually, you probably could figure it out just by looking at this, what the next one is going to be. So, but here, let's go back here. So we've got 1/2, 1/6, 1/24. Yeah, you got it? Yeah, either way.
So it's just for 1/2, it's multiplied by 1/3, and then multiplied by 1/4, and then by 1/5.
So it'll be 120.
And then 1/7, 1/7.
1 over 720 is next after that. Very nice. So we see this pattern. There is a pattern, and if I could just write that pattern down as a power series, then I have the power series representation for e to the x. Let me pause, though, and say that this is actually pretty good. We've done a pretty good job. Remember that this thing converges. It converges. I'll just put this near. I'll put near x equals 0. I don't know how near it is. We would have to work out an interval of convergence. We'll deal with that next time. But for now, let me just mention, it converges when you're close to x equals 0. In fact, let me show you what I have here. In fact, I didn't go as far as, I got a little excited. Let me just update my computer here. So plus x to the 4th divided by, wait a minute. Divided by 24. Okay. Okay, so let me just show you what I've drawn here. This here, this is the graph of, and it's kind of hard to tell. Let's see, can I make this any bigger? Probably. Oh, there, it's bigger. Okay, they look exactly the same. Just a minute. I need to make them look different. Let me get rid of this color here. I said color blue. You could do this on Desmos or whatever. Okay, now you can't see the green, but the red here, the red is e to the x. You're familiar with e to the x. It looks like that. The green, if you could see it, which, I wonder if I can, well, let me see. I don't know the syntax here. Let's see. Color is equal to red. How about if I do it in parentheses? Red, comma, blue. See if it does. No, it doesn't like me. Okay, I guess we're stuck with that ugly green. I'll do it in blue. There, and then we'll be able to see it. Okay, so you can kind of see, but it's harder to distinguish the two, and it's because when you're close to 0, the polynomial, this is the polynomial that we have. Where is the polynomial? It's this polynomial. That polynomial on the right, that polynomial is this curve. It goes below here, and then it goes above there. That is the polynomial, the 4th degree polynomial, and notice that it's very close. It's very close to the e to the x in this interval that I've got showing here. In fact, I could widen the interval a little bit. Let's see if I do that. Go from -3 to +3. And it's still pretty close, except for at the very ends here. Like over here, it's kind of separating out. Because we have this polynomial that's pretty close to the actual truth of e to the x, we're going to have a name for this. So even though our goal eventually is to talk about a Taylor series, this particular polynomial, this is called a Taylor polynomial. So Taylor polynomial around x equals 0. So just to explain the language, Taylor polynomial means that I'm going to stop this series business at some point, and then x equals 0 tells me how far out, or no, what the center is going to be. So this is centered at x equals 0. I've got a formula for this. I hope I don't, well, it's all right. So let me just show you the formula. Yeah, well, it's the way it is. I've got the PowerPoint. We'll do it. So that's scary. Where is the formula? No, we don't want to do this. Just a sec. There it is. That's the formula. And I know that looks even worse than what I had up on the screen. But this is the formula for what's called the Taylor series. But I don't want you to deal with the whole Taylor series for tonight. For the homework, we're just going to be dealing with a Taylor polynomial. So this is the important bit, though, is this right here. So let's see if I can find a good example of this. How about if I just make one up? Yeah. Okay, that's the important bit, though, right there, is that formula. So you'll notice this in factorial. In factorial, it kind of popped up in the e to the x example. This business we have to explain, but it has to do with the fact that you're repeatedly doing the derivative to figure out what the coefficients are. And the coefficients always end up being the nth derivative divided by that in factorial. And then the a is just where are you centering this thing. Like I said, I got a video to show you in just a bit, but we need to do at least one more example before we do the video. So let me do, let's see, a little bit harder example than e to the x. Don't worry, I'm just going to write this down here. Here we go. So this is the Taylor series. Is this thing f so to the n of a over n factorial x minus a to the n. Okay, so that's the general Taylor series formula, but here's all I want to do is I want to do this. I want to find the Taylor polynomial. So a Taylor polynomial, we're going to do something like this. We'll have t sub, I guess t sub n. That's not the greatest, but we're going to do it. And this is going to be, I'll use k here instead of n. So go up to n of f k of a over k factorial. Sorry, I had to change the index to k to make this work. But that's a Taylor polynomial. It just means take the Taylor series, chop it off. We'll deal with this more next time, but for now, I just want to do one more example of this, then I'll show you the video and we'll call it a day. So Taylor polynomial, you're just chopping this off. And so here's how I would suggest you do this. Let us try this. Let us do the Taylor polynomial. Let's do the fourth Taylor polynomial, t sub 4, for the function. Let me just make sure that this isn't too crazy. How about, I guess square root of x isn't terrible. So we'll use square root of x for f of x around x equals, how about 9? So I want the fourth Taylor polynomial for this around x equals 9. So let me just dissect this for you, because I know it looks so crazy. And up here, it looks like we did something different, but let me just reassure you, we're going to repeatedly do derivatives. It's just that x to the, this square root of x is not as nice as e to the x, but we're going to do the same thing. So step 1, do the derivatives. Step 2 is plug in x equals a, and then step 3 is write the Taylor polynomial. So that's what we're going to do. So let's do our derivatives first. Since this says t sub 4, I'm going to need to do 4 derivatives. So here's what I'll do. I have f, and then I'm going to do f in evaluated at 9. Okay, so we start off with the 0, which is just the function itself. square root of x, and over here, the square root of 9 is equal to 3. So I'm just making a table for myself. If it helps you, you could put an in over here, 0, 1, 2, 3, 4, so that you can keep track. Here, just a minute. I need to move that over just a bit there because some of you will benefit from this. Okay, let's do our derivatives first. So I need to do 4 derivatives, and hopefully we can see a pattern that will emerge. Maybe not. We'll find out. So first off, who are we going to bug? How about Claire? Claire, what's the first derivative of this thing? Oh, yes, 1/2 x to the negative 1/2. That's perfect. All right, Morgan, what about the second derivative?
Negative 1/4 x to the negative 1/2.
Okay, we're doing great. Third derivative. We got Zechariah. What do you got here for third derivative?
Negative 3/8 to negative 5/2.
5/2, very good. And it's positive 3/8 because you're multiplying negative times negative. You use the positive, but you got that. Perfect, good job. And then let's get the last one, the fourth derivative. Who gets to do that? Some newbie. We got to re-randomize. Sawyer gets to do it. Sawyer, what do you think that fourth derivative is? Nice, nice. Okay, now we have to plug in whatever it is that we're doing here. In this case, it's x equals 9. So let me do this for you. Remember that a negative exponent, a negative exponent like you have here, and all the rest of these, that just means put the answer in the denominator. So hopefully you can do this sort of in your head, but if you need to, you can write it out. I just want to make sure that I have enough room for everything. So this ends up being 1/6, because it's going to be 1/2 times 9 to the negative 1/2, which is 1/2 times 3, because the square root of 9 goes in the denominator. So here this is going to be 1/4 times 4 times 27, because 9 to the 3/2 is 27. Whew. See if I can do this. 9 to the 5/2 is 243. So this will be 3/8 times 243. Oh no. 9 to the 7/2 is 2,100 and something. 87? 2,187? Okay, that one I don't have memorized, but apparently I pulled it out of somewhere. I dug deep. 2,187. Whew. Okay, so all I did there was I plugged in x equals 9. So now, the last step, I know it says just T4 there, but what you're going to do is you're going to build T4, you're going to build this polynomial from this formula. And that formula looks scary, but it's not as bad as it looks. I will get it started. So we do the start at k equals 0. K equals 0 is the 0th derivative, which is just, I guess, 3 here. So it's going to be 3/0 factorial times x minus 9 to the 0th power. So that's the 0 term, k equals 0. Now we're going to keep going until we get to 4. The first term, that's going to be 1/6 over 1 factorial times x minus 9 to the first. Then the second term, 1/4 times 27, which is 108, all over 2 factorial times x minus 9 squared. Then you have 3/8 times 243, all over 3 factorial x minus 9 to the third. One more term, negative 15 over 16 times 2187, whatever that is. all over 4 factorial x minus 9 to the 4th. That is the Taylor polynomial around x equals 9 for this particular function, for square root of x. Wow, it looks super complicated. A couple of things to note though. Check it out. After this term, after the very 0th term there, this is an alternating series. And you know it's going to keep alternating because you always have this negative exponent that you multiply by. The next one is going to be a positive, then negative, then positive, negative, positive. So this is alternating. You see those factorials there, and those factorials, they basically came from this place right here of doing the derivatives. And so you can kind of see the factorials developing here. You have 2, which is 2 factorial, 6 is 3 factorial, 24 is 4 factorial, 120, which we didn't have here. Oh yeah, there it is. 120 is 5 factorial. It comes from doing the derivatives of a series. So that's where those factorials come from. And then finally, even though it is not obvious, there is a pattern. And you can kind of tell me what that pattern is. You see that it's always going to be, 9 to the, but the reason I knew that this was 243 is not because I knew what 9 to the 5 halves was. It's because I know what 3 to the 5th is. This is 3 to the 5th. This is 3 to the 7th. The next one will be 3 to the 9th. And so you can start exploiting or finding the pattern. There is a pattern. We're not going to work on that yet. That'll be for future. But there is a pattern. This is called the Taylor polynomial. We aren't even going to worry about convergence. There is a convergence, interval of convergence. But that is the Taylor polynomial. Okay. We have 2, well, I promised you a video. I'll save that for last. That way you won't pack up too early. So let me just pull up the homework because I want to show you that it is not as bad as this. This is worse than your homework. Give me a sec here. Pulling up homework. And then we'll do the video because the video is great. Wait a minute. Hold on. Hold on. Oh, okay. I was in the wrong week. Here it is. Taylor and Maclaurin series for Tuesday. Let me pull this up here. You can see it in just a sec. Hold on a minute. Here we go. Okay, I don't know what this means. That's dumb. Okay, so here we are. Make this big. So you'll notice that we want to find the first few Taylor polynomials. Notice that it just asks you what is f of 0 for this function and what is f prime of 0. It's just walking you through what we just did. So don't be scared of that. Just do what we did in class here. And then it asks you what is the first Taylor polynomial. So that's where you have to build this. You're going to actually build it based on your derivative at 0, and then the second derivative will go into the Taylor polynomial, the second one. So that's sort of what we did, but it'll be an easier one. Here, this, 4/3, but it's the third Taylor polynomial, so you're not going to have to go quite as far as we did. So you do your derivatives, plug in x equals 6 to get the coefficients. So here again, wow, actually these are kind of nasty. Well, they're there now. Product rule. Okay, so I apologize ahead of time. Okay, so here, let me just go back really quick and to set you up for the video. Where is my video here? Here it is. So first off, there. You remember the very first thing we did was e to the x? Well, I don't know if you are like me, but whenever I hear Taylor series, all I can think of is Taylor Swift. And so it would be nice if Taylor Swift would help us with this. And in fact, someone went and asked her all these questions. So here it is. Let's see if the volume is up. We'll find out.
So this is the Taylor series. The tool we use in math because
Remember, a polynomial is just a combo of numbers and variables under this raised to different powers.
All right,
Can we just work through an example?
Sure, let's do it for e to the x. The purple curve up there is how it's going to look.
Okay, so how do we break e to the x down?
So this here is the formula for the Taylor series, and to rebuild our function, we just gotta find each of these terms.
Wait, what is that letter a?
It's basically whichever position along the x-axis we build the polynomial around. So as we start adding these terms, A is the spot where our creation will be most accurate.
Let's just set it to 0 for this example and watch what happens.
Hang on, x minus 0 is x.
Nice simplification, Doc.
Now, before we go any further, remember the derivative of e to the x is also e to the x. This means that the second derivative, which is the derivative of the first derivative, will also be e to the x.
And so will the third derivative, fourth derivative, and all the others.
So for that first bit, f of 0 is just e to the 0, which is 1, right?
Yeah, exactly. And all these derivatives with 0 plugged in will also be e to the 0, so they'll also all simplify to 1.
Wait, but what's up with the exclamation marks?
That they just mean factorial. So the 2 factorial is 2 times 1, and the 3 factorial is 3 times 2 times 1, and so on.
Okay, now check this out. Here's our Taylor series with the first term, second term, third term, fourth term, fifth term.
And if Elon keeps adding these terms forever, eventually we'll end up fully recreating e to the x.
So, there you go. I guess that's it for today. And so stick around if you need to complain about your exam. I'm going to stop the video so that no one else can hear your